Hello, in this video we will talk again about position, velocity, and acceleration, but this time in angular terms. So far we have talked a lot about translation. This object moves from here to here. But in these videos, we will start talking about rotation. Okay, so something spinning about an axis. For this, we're going to use a very special model, is the model of a rigid body. A rigid body is a body that does not deform. So that's the condition, that's the assumption we're going to use to understand how things rotate. Zero deformation, or at least negligible deformation. So consider this Blu-ray disc. We are going to define a position. We're going to first use a particle P located at a distance r, radius from the axis, rotation axis O, right? So this is the reference line, and then as it rotates, we understand how point P moves through an arc length S, right? It keeps its same radius, but now it has an angular position equal to theta. So for this position here, we're going to say that the initial angular position, the initial here, well, is theta I, which let's say here is 0. And then we're also going to have a position angular final, which is just whatever we measure this angle theta. This is in comparison to linear position, which was initial position and final position, right? But angular position is measured in degrees or in radians. I believe I already explained what a radian is in a previous video. In any circle, remember that for any arc length S, right? Oh my God, this is so hard for me. That there's an angle theta and then the radius r. There is a simple relationship between the three quantities. The segment or the arc length S is just theta times r. Hence, theta could be S over r. When you have a distance of S equal to 1 meter and a radius of 1 meter, or 3 and 3, or 7 and 7, the ratio, the ratio is 1. Theta is equal to 1 nothing, but we say 1 radian. The units will cancel. So when the segment is equal to the radius, the angle theta is equal to 1 radian. That's the definition. So if S is equal to theta r, well, there's a lot of things we can say. Look, first, we got angular position. So what about angular displacement? Is going to be delta theta. So final angle minus initial angular position, which is just the equivalent of linear displacement, position final minus position initial. I am going to define something called angular velocity, which is just how many, like here, just remember velocity was delta x over delta t. So I am going to define delta theta over delta t as the angular velocity, right? How many degrees per second, right? How many degrees every second does my particle cover? right, as it moves in circular motion. And the symbol for the angular velocity is the Greek letter omega. So this is my definition. Omega is a delta theta over delta t, and this is the average angular velocity. You see the analogy with the linear angular velocity average. Ugly. Average, right? We had the instantaneous, remember? The instantaneous, which is dx over dt. Well, the instantaneous angular velocity is going to be d theta over derivative of theta, or with respect to the derivative of time. There you go. So what is that? Let's continue here. This is our angular quantity. This is going to be our linear quantity. So the instantaneous is d theta over dt. But remember that, well, we're going to leave it like that. As opposed to v is dt, dx over dt. Okay. In the previous slide, degrees, this will be in meters, right? Degrees or radians in meters. Displacement in meters, displacement here in degrees or in radians. Same thing, this is meters per second units. This will be either degrees per second or radians per second. And I'm just going to keep it in radians per second, knowing well we can convert between degrees and radians. So here as well, radians per second for the instantaneous, or meters per second. Remember that 2 pi radians is 360 degrees. That's the conversion factor. So again, to understand the concept of angular velocity, you start at position A, you move to position B in rotational motion, covering an angle difference of final minus initial theta in an interval of time final minus time initial. So that's what this quantity means. And in the same way, we can define an acceleration average of change in velocity over change in time. We can define an acceleration angular, so angular acceleration, and we're going to use Greek letter alpha. For the average is going to be delta omega over delta t, and the instantaneous will be d omega over dt. So if here we had meters per second squared, here we're going to have radians per second squared. Now, a few things. You see, if we say that this particle moves from here to here, you see, this is initial position and then goes there, that's angular displacement delta theta. Notice that this particle, another different particle in the disk, moving through this distance, through this segment of arc here, has the same delta theta. See, both have the same delta theta. Is the same for everybody. For this particle or this particle or this particle moving from here to here, they move through the same angle. So if delta theta is the same, that means that, well, this particle gets here at the same time that this particle gets here. So that means omega is also the same and alpha. So all three quantities, angular displacement, angular velocity, and angular acceleration, are the same for all three particles in this rigid body. Remember, no deformation. But the same is true, for instance, for this guy. This particle that moves from here to here, you see, is the same angular, is the same delta theta, is the same omega, and is the same alpha. So for the same time interval, any particle, no matter where it is, will have the same delta theta, the same omega, and the same alpha. What this is telling us is that these three quantities, angular displacement, angular velocity, and angular acceleration, are the same. All three quantities are the same for every particle in a rigid body. Now, another important thing to consider is that this thing is going in this direction, as opposed to going in the opposite direction. So you see how direction is important, and that means angular acceleration, angular velocity. Well, I'm going to put it here. Displacement, displacement, velocity, and acceleration are vectors, right? Because it's not the same thing to be going in this direction or to be rotating in this direction. This direction is positive and this direction is negative. If the rotation happens counterclockwise, we say positive. If the direction of rotation is clockwise, we say is negative. The origin of this is basically, if you are in the XY plane and then you have the Z axis. So if you have this type of rotation, which is, as I said, is counterclockwise, and I told you is positive, well, we actually assign the positive vector in the direction of Z. We will say is positive in the Z axis, right? So we will say when angular velocity is positive, we assign the positive k unit vector. If the rotational motion is negative, like so, then we assign a negative sign, and we say is negative in the z-axis or in the negative k direction. In class, I'm going to show you how to find this following something called the right-hand rule. But we'll do that in class. So we're going to practice this in class, but here you have a nice diagram that tells you how things spin. So you create this shape with your hand, and then you move your fingers in the direction of the rotation, and the thumb tells you if the rotation is positive or negative. If it comes out of the plane of rotation, we say positive, like here. If it goes into the plane of rotation, the thumb, then we say that rotation is negative. So these are the main definitions for angular position, displacement, velocity, and acceleration. And as you can see, they're just analogous to what we did for linear motion. In the next video, we will talk about these quantities under constant angular acceleration.